Okay, let's look at some inelastic collisions. So now we have two objects that are colliding and are sticking together. Okay, there's no separation like in an elastic collision. In elastic collisions, they are not separating. Okay, which means that after they collide, their masses will combine to form a larger mass, and they will share a common velocity, which is represented here by my equation. So m1 plus m2, after they collide, their masses are combining and they are sharing one common velocity. Okay, my example says that a 1,500 kilogram car is traveling at 15 meters per second to the south, colliding with a 4,500 kilogram truck that's initially at rest. The car and the truck stick together, telling us it's an inelastic collision. Afterwards, what is the final velocity of the two vehicle mass? Okay, so using the box method, I'm going to go ahead and draw boxes for the car and the truck. And then once they collide, they are going to form one combined mass. So there's only one box after the two objects collide. So inside the boxes, I have the masses. So I've got a car with a mass of 1,500. I've got a truck with a mass of 4,500. And combined, they will form a mass of 6,000. So 4,500 plus 1,500 gives you a combined mass of 6,000. Now, above the box is their velocities. Well, my car is traveling 15 meters per second to the south, which is in a negative direction. So the car has a velocity of a negative 15 meters per second. The truck is initially at rest, so its velocity is 0. We want to figure out the final velocity of the two vehicle mass, so we want to solve for this VF. Okay, so since momentum is conserved, if I can find the individual momentum and then add up and determine the total, I can find the total momentum before and the total momentum after because they will be equal to each other. So using the equation P equals m times v, I'm going to use the mass of the car times the velocity of the car, and the mass of the truck times the velocity of the truck. So what you're looking at here is the two vehicles before they collide. I should have wrote this before, but this is before, and this is what's going on after they collide and stick together. Okay, so momentum is mass times velocity. So 1,500 times a negative 15 gives me a momentum of a negative 22,500. And then my truck, 4,500 times 0, anything times 0 gives me 0. So if I add those two together, if I want to get a total, I'm going to take negative 22,500 and add 0 together, and that gives me a total momentum of negative 22,500, which means that the total before they collide is equal to the total after they collide. So the total after they collide is also negative 22,500, which means all that momentum is in the car truck mass that is combined. So now that I have the combined momentum, I have the combined mass, I can figure out their combined velocity using my P equals mv equation, where momentum is now negative 22,500 the mass is 6,000, and velocity, final velocity, is what I need to solve for. So if I want to get VF by itself, and it's multiplied by 6,000, I need to divide both sides by 6,000. Those cancel out, and I get a negative 22,000 divided by 6,000, which is a negative 3.75 meters per second. That is the final velocity of the two cars, the two vehicles combined. All right, today I'm going to do a couple examples. One, I'm going to do an elastic collision example, and then I will do an inelastic collision example for you using the box method. Now, I've already showed y'all the equation here for elastic collisions. You're multiplying the masses and velocities of each object before the collision, and then the masses and velocities after the collision, and you're comparing their overall momentum. Now, the total momentum should stay constant because momentum is conserved. So the total momentum that you can find before the collision will equal the total momentum after the collision. Now, if you like using the equation, then by all means do the equation. I'm just going to show you a different method, and it involves using boxes to help you visualize a little bit better. Okay, so in this example, I've got a bowling ball with a mass of 4 kilograms moving to the right. I've got a bowling ball 5 kilograms at rest. The moving bowling ball will hit the resting bowling ball. They will collide, and then they will separate. We ultimately want to find the velocity of the second ball after the collision. Okay, so I'm going to start off by showing y'all the box method. Okay, so I'm going to draw the boxes that are going to represent the actual objects, the bowling balls here. So I have two bowling balls, so I'm going to draw a box to represent one bowling ball and a box to represent the second bowling ball. Now they're going to collide, and then afterwards they are going to separate. So I have the same two bowling balls before and after. Okay, now I'll label this as before and after for you. Here we go. All right, so the left side of my diagram here is going to be before the collision, and the right side will be after the collision. Okay, so what's going to go inside the boxes is the mass of each. Okay, so I've got a bowling ball of 4 kilograms. So inside the box, on the first box on the left, I'm going to write the mass of 4.0 kilograms. The second bowling ball has a mass of 5 kilograms. Okay, now their masses will not change. So even though they collide with one another, their masses will not change. So this is again 4 kilograms, and this is a mass of 5 kilograms. Okay, now above the boxes, I'm going to write their velocities. How fast are they moving? Okay. All right, so I'm going to write the velocities on the top. The first bowling ball with a mass of 4 kilograms has a velocity of 8 meters per second to the right. So its velocity is 8 meters per second. And it's colliding with another bowling ball that is at rest. It's stationary. So it's got a velocity of 0. After they collide, the 4 kilogram bowling ball has a velocity of 0 because now it is stopped. It is at rest. And we ultimately want to find the velocity of the second bowling ball after the collision. Okay, so we've got the masses and the velocities of each. Now, what's going to go below the boxes are their momentum. Each bowling ball has momentum. And remember that momentum is mass times velocity. Okay, so momentum equals mass times velocity. If I look at this first bowling ball, it's got a mass of 4 and a velocity of 8. When I multiply 4 times 8, I get a momentum of 32. Okay? The second bowling ball, mass times velocity, 5 times 0 gives me a momentum of 0. Now, the total momentum before the collision is as simple as taking my 32 and adding 0. The momentum of the 4 kilogram ball in addition to the momentum of the 5 kilogram ball is 32. 32 plus 0 is 32. So right here at the bottom, I'll write total momentum, or total P, equals 32. Now, because momentum is conserved, whatever momentum I have before the collision, I'm going to have the same momentum, total momentum, after the collision. So the total momentum after is also 32. Okay? Now, up above that, I know the mass and velocity of this bowling ball, so I can again calculate that momentum. So 4 times 0 gives me a momentum of 0. So if the total momentum is 32, and this has a momentum of 0, then all that momentum had to be transferred to this bowling ball. So its momentum is 32. Okay, so now that I have the momentum of this bowling ball, I have the mass of this bowling ball, I can solve for the velocity of this bowling ball. Okay, using my momentum equation. And that momentum equation says P equals M times V. Well, if my momentum is 32 and my mass is 5, velocity is what I need to solve for. Well, to get V by itself, I need to do the opposite operation, and that is to divide by 5 on both sides. So these 5's now cancel, and that gives me V all by itself, and 32 divided by 5 gives me 6.4 meters per second. That is the velocity of the 5 kilogram ball after the collision.